In this Lab 6, our final lab, we'll pick up where we left off the last time. So when we left off the last time, we were looking at distributions and we were examining genome histogram. In this lab, we'll begin by looking at 3 additional genomes: genome box plot, genome jitter plot, and genome dot plot for examining distributions. Then we'll think about facets, and finally how we can insert lines of best fit onto a scatter plot. So the first genome for looking at distributions we're going to look at is genome box plot. And here we have a box plot. I want to go over this box plot because different packages make their box plots differently. So what we can think of is on this axis, we would have some continuous variable such as city mileage. And so when we've got a box plot like this, there are a number of things to focus on. The first is this thick black line. This thick black line here represents the median, such that 50% of the values in the data frame MPG would be greater than that, and 50% of the values of city mileage in the data frame MPG would be less than that. By default, box plots do not show where the mean is. If you want to put a mean on your box plot, go to Appendix A1 and you'll see how to do that. This line here is the upper hinge. 25% of the values of city mileage would be greater than the upper hinge, and 75% would be smaller. This is the lower hinge. This is the lower hinge. 75% would be greater. 25% would be smaller than the lower hinge. So if you think about those two bits of information together, 50% of the values of city mileage in the data frame MPG would lie within this box, within the upper and the lower hinges. We've also got these things that are known as whiskers. There's one whisker and there's another whisker, and the length is defined as the largest value within 1.5 times the underquartile range of the upper hinge. So, in other words, you'd start here, you'd multiply the interquartile range, and this is the interquartile range, multiply that by 1.5, add it to this hinge, and go up there. In terms of the lower whisker, you'd start off here, take this interquartile range, multiply it by 1.5, add it to this point, and go down there. And then any points outside of this are viewed as being outliers. So what's really all this business about whiskers and outliers? The way I understand it is that if one had a normally distributed variable, then 95% of the values would lie within here, and the remaining 5% might be considered outliers, and they would be represented as dots. So in this slide, what I want to do is compare a box plot with a histogram. And this box plot is based on a built-in data frame called Diamonds that has many, many records. And I wouldn't worry about what's going on down here, because in this data frame Diamonds, there's a bunch of diamonds and they have different cuts, and the data here are shown for a particular cut called ideal. But basically, we've got a whole bunch of diamonds, and we're interested in demonstrating what the distribution is of prices. So this thick line here shows us that the median price for these diamonds looks to be about $2,000. And if we think about our interquartile range here that forms this box, it would appear that about half the records in this data frame, about half the diamonds, would lie between a value of about 1,500 perhaps and a little shy of 5,000. So we can compare that with a histogram. So to take this histogram, I've rotated it 90 degrees. So what I've done is I put count on the x-axis, and now price is on the y-axis, and the price here lines up with the price on the box plot. And you can see that if you follow some of these things across, you can see that the 5,000 here corresponds to 5,000 here, and the 10,000 here corresponds to the 10,000 there. So if you think about some of the differences between a histogram and a box plot, one of the things about a box plot is that the median value such that 50% of the records will be greater, 50% will be less. The median value is explicitly identified in the box plot, but it's not clear where the median is in a histogram. On the other hand, with a histogram, you get a little bit more detail about the distribution. So for example, you can see that there's kind of a modal value right about here, and that certainly isn't evident from the box plot. In both cases, you can see that the distributions have a bit of a tail. So in the histogram, you can see this long tail here, and in the box plot, you get evidence of a long tail because this long whisker and this whole bunch of outliers. So our goal with Geom histogram is to make a plot that looks like this. So for our 3 drives, the 4-wheel, front wheel, rear wheel drives, we're interested in highway mileage. We want to make that plot. The code is pretty straightforward. We're going to use the data frame MPG. We're going to inherit that data. We want drives on the x-axis. We want highway mileage on the y-axis. There's one option you might consider, and that's var width equals t. If you put that in, the width of the box will be proportional to the number of observations. The stat's okay, but it's a little bit tricky. You don't have to worry about it. It operates in the background. But just as a reminder, we talked about stat earlier. And remember, for geom point, for geom line, and for geom call, what was the default stat? The default stat was identity. And that worked really well by default because what went on the y-axis was identical to whatever we specified as the y variable. In contrast with geom histogram, the default stat was bin, and as you recall, it would take whatever variable we mapped onto the x location, take that variable, chop it up into bins, count the number of observations, and the count went onto the y-axis, and that's why with geom histogram, we never have to specify what the y variable is. So, how does it work for geom box plot? For geom box plot, it's a pretty complicated stat. We don't have to worry about it. It works okay by default, but what it actually does is it's going to take this variable highway mileage that we specified as our y variable, and it's going to calculate a bunch of statistics, the median, the interquartile range, etc., and that's what's going to go on the y-axis. In terms of position, the default position is just fine. So in terms of specific code, if I want to make this plot, it's really not that complicated. I specify my data frame, MPG. I want drive on the x-axis, and I want highway mileage on the y-axis, and that's what we get. One slight modification is this code here is the same, except now I've added var width equals t, so that the width of this box, this width, is now directly proportional to the square root of the number of observations. So you can see that there are fewer rear wheel than there are front wheel or 4-wheel. So in fact, there's 103 here, and 106 here, and 25 here. So these two widths are about the same, and this box is much thinner. Geom jitter is without a doubt my absolute favorite geom. And the reason I like it is that with fairly small data frames, if I've got maybe 300 records or fewer, geom jitter is really a nice way to get the maximum possible information from that data frame. So the advantage of geom jitter is if you think about the data frame MPG, how many records does it have? It has 234 records. And by using geom jitter, each one of those 234 records is shown. So you got 234 dots here corresponding to all 234 records, and the y value that's shown here is in this case reflecting the actual highway mileage. So you can't get any more detail than this. And so if I look at this plot, I can draw a number of inferences from it. I can look, for example, at the 4-wheel drive, because I've got drive on the x-axis, and I've got my 4-wheel, front, and rear-wheel drives. I can look at the 4 wheels and say, hey, this looks almost bimodal. It looks like there's a little clump here, and a little clump here, and perhaps an excluded middle here. I look at my front-wheel drives and say, yeah, it looks sort of normal, but perhaps, some skewness in this direction. And then when I look at my rear-wheel drives, what's very obvious is that I've got far fewer rear wheel than either one of these two guys, and also the distribution appears uniform. So if you want to really get a detailed sense of what's going on with your data, I would strongly recommend using GeomeJitter. So in terms of its general syntax, we'll once again look at the template we've seen so many times before. We're going to specify our data frame and inherit it. Drive is going to go on the x-axis, and highway mileage is going on the y-axis. There's a number of options we want to consider. Two of those are size and alpha. Size determines the size of the marker. Alpha determines the transparency of the marker. And so typically what you'll do is you just play around with those things until you get something that looks nice. In terms of the default stat, it's just fine. Position, you will want to use a position statement, and it's going to have a form that looks something like this. And remember the way the fonts work, everything that's in Courier, you reproduce exactly like that. So most of this will be produced exactly as shown here. The only things you're going to get to change are these two numbers here. The height, as we're going to see, you'll typically set to be equal to 0. The width, you'll just play around with until you get something that looks nice. So let's look at some of these things. The idea about size and alpha are the markers. Size determines the point size, and alpha determines the transparency. The way transparency works is absolute blackness has a transparency of 1. If you set alpha to equal to 0.25, then you'd need 4 points on top of each other. 4 times 2.5 is 1, so 4 points on top of each other would give absolute blackness. In terms of our position statement, this is the general form it's going to have. All the words will be typed in exactly like this, except that there's these two numbers here. The second number, the height controls the amount of variability that's introduced. In the y dimension, you'll set that to 0. Width determines the amount of variability. In the x direction, you'll typically set that to some number that will make your plot look nice. So here's some examples of manipulation of size and alpha. So I've made the size fairly large. I've set the alpha is equal to 0.1. So I'd need 10 points sitting on top of each other to get perfect blackness. Here I've set the size is equal to 4. Alpha is equal to 0.5. 2 dots on top of each other would represent perfect blackness. Here the size is smaller than the default. The default's 2. I've set it to 1. There's the default alpha. Here the size is 2 and the alpha is 0.1. So essentially, you just play around with size and alpha until you get something that looks like nice. Actually, in most cases, you don't have to use alpha. In most cases, you can get a pretty decent result by manipulating your size. But if you got an awful lot of points, then yeah, sometimes you are going to have to use alpha if you got a lot of points that are sitting on top of each other and you want to indicate that. So this particular plot looks at this idea of the position statement. And the whole idea of a jitter plot. The word jitter reflects the fact that with jitter plots, that there's variability that can be introduced either in this direction by the width statement, or you can introduce variability in this direction by the height statement, and it's a question of getting those two things right. Alternatively, you can just ignore me, and you can ignore putting in this statement, and if you don't put in that statement, you'll get something like this, which you just get these scatters that are very hard to interpret. This example here reflects probably the worst possible thing you can do. So I've set the height equal to 0.5. So what's that going to do? Well, the whole idea of GeomeJitter is that it introduces random variability into the positioning of the points. And if you set height is equal to 0.5, that indicates that the random variability that's inserted is inserted in this dimension. So each of the variables, each one of these values of highway mileage is going to have some random up and down variability associated with it. And that's exactly what we don't want. Because what we want is, for each one of these dots, we want the Y location to exactly reflect highway mileage. So we don't want to insert any variability in the vertical direction. The other thing we've done that's made this thing useless is we've said the width equals 0. So width inserts random variability in this direction. Well, we've inserted no random variability in this direction. And since we've inserted no random variability in the horizontal direction, we can't tell what the heck is going on. Down here is still kind of useless. The height is equal to 0, and that's good because we're not wanting to insert any variability in this direction. So as a consequence, each one of these Y values reflects the actual highway mileage. What we have done, however, is we've set the width as too wide. So we've put too much variability in the horizontal direction, and it's very difficult to see what's going on. The sweet spot occurs, in my mind, here. We've set the height is equal to 0, and that's what we're almost always going to do because you don't want any variability inserted in the vertical direction. And by choosing the width equal to 0.1, and that I typically arrive at this value through trial and error by setting the width is equal to 0.1, it inserts a bit of horizontal variability, call it jitter, in this direction. You get some separation of the points so you can see clearly where those clusters are associated with the forewheel, the front wheel, and the rear wheel drives. So here's just some output. Data frame MPG, drive on the x-axis, highway mileage on the y-axis. There's my position statement. As always, height is equal to 0 because I don't want any variability inserted in this direction. And these other three things, size, alpha, and width, I just played around on a trial and error basis and got something that I thought looked reasonable. Just a note, if you're going to use transparency, in other words, if you're going to use that alpha equals, what I found was if I made a plot like this that's got some transparency in it, and I copied it to my clipboard with the idea that I could paste it into a PowerPoint presentation, oftentimes it didn't work. So if that doesn't work, there's a couple of things that you could do. One is you could do it as save as image, and alternatively, you could refer to previous slides where we talked about this arrange GROB function. That seemed to work pretty well. So the last geom for examining distributions that I want to look at is geom.plot. And geom.plot is a little bit like geom jitter in that if we look at the data frame MPG and we're interested in highway mileage, each one of those 234 data points in MPG, its highway mileage is going to show up as a separate dot. On the other hand, there is some loss of information relative to geom jitter in the sense that bins are created. So there's a bin created there with a number of observations and a bin created there with each dot representing a single observation, and the same thing here, a bin with each separate dot representing a separate observation. So there is some information loss. However, relative to geom jitter, dot plots are a little bit more conventional. So what you might want to think about doing is that in order to understand your data, you use geom jitter. And once you have an understanding of what those distributions actually look like, you could use a more conventional plot like geom.plot to represent that distribution in your thesis or journal publication. So the code for making a dot plot, we specify the data frame, and we inherit the data frame. We say we want the drives on the x-axis and highway mileage on the y-axis. Now, in terms of our options, the first two I don't really consider it to be that optional. You'll definitely want to use this. And you can see they're in Courier, so we produce them exactly as shown here. Bin axis equals y, and stack dir stands for stack direction is equal to center. And we'll go into a little bit more detail on those in a moment. Geom.plot uses bins. And so, as I said with geom histogram, you might want to play around with bin width equals n and make sure that your conclusions are robust, that you're not getting artifacts occurring in the appearance of your plot as a consequence to your particular choice of bin width. There's also this thing called dot size, and dot size controls the size of the markers in the dot plots. One thing you note, when we had geom point, the size of the markers was determined by size. Now the size is determined by dot size. Also, the funny thing about dot size is that it's relative to bin size, and the numbers tend to be quite small. So if you use a really big number, you're going to get something that's really ugly. The other thing about dots controlled by dot size is they work just like those rectangles in the sense that because their shape is 21, fill determines the obvious color, and the word color just determines the border color. So here's an example using the data frame MPG. Drive goes on the x-axis, highway mileage goes on the y-axis, and these two things here, as I said earlier, You put them in just like that in Courier, no change. The bin width, you can play around with that, and I've set the dot size to be equal to 0.3. Notice it's a fairly small number. Big numbers are going to look pretty ugly. And so we can see the idea of this bin axis equals y. This idea of bin axis equals y is we're creating a series of bins. We're creating a series of bins relative to the y-axis. And so these numbers here were put in PowerPoint. They weren't put in ggplot. But essentially, we've created a bin that goes from 13 to 15. And if you count up these little dots, you see that there are 11 records that fall into that bin that extends for highway mileage between 13 and 15 miles per gallon. The whole idea about this stack direction equals center is you've got a cluster of points here that are centered over the 4. You've got a cluster of points here that are centered over the F, and a cluster of points here that are centered over the R. So in this slide, I want to focus a little bit more detail on some of the features that we saw in the previous slide. So this is the code that produced the plot that we just saw. Bin axis is equal to Y. You'll almost always use that because you want to have the bins going in this direction relative to the y-axis. And stack direction is equal to center because you want these points centered over the different values of drive. And then I've specified my bin width and my dot size. So I've made some modifications in this code to produce this plot. Bin axis is equal to y. I'll almost always, I can't think of any reason why I would want to change it. Typically, I do use stack direction equals center. You might want to think about stack direction equals up. I don't particularly care for it. What stack direction equals up does is it left justifies the cluster of points. So the cluster of points here is left justified here, left justified here. In this particular case, I don't find it very attractive. Bin width. Geom dot plot uses bins, just like geom histogram. Anytime you're using bins, you probably want to play around with bin width and make sure that the appearance of the plot really represents what's going on with your data. So here I've set the bin width equal to 2. Here I've set the bin width equal to 4. Here you can see I've got a fair amount of detail. Here you can see the results are fairly coarse. I'm pretty sure I would prefer these. In terms of dot size, the thing about dot size is that the relationship between dot size and the actual size of the markers is linked to bin width. So it's kind of strange. In practice, what I will do is trial and error to get a bin width I like, then trial and error to get a dot size that I like. So we can see in this instance, I had a dot size specified as 0.3, and that gave me a particular marker size. Bin width and dot size are linked. So when I went from here to here, I doubled the bin width. If my goal is to have the marker size here and here to be the same, since I doubled the bin width, in order to have the marker size here the same as the marker size here, my dot size is going to have to be 1/2 as large. So everything we've seen up until now, we've been focusing on highway mileage, a continuous variable. But what if we just wanted to know, hey, how many records are there for each of the 3 different drives? In other words, we're no longer focusing on a continuous variable, but rather a discrete variable. I just want to know for each one of these drives how many observations there are. The geom we can use for that is geom bar. Now, in the past, we used to use geom bar to make column plots. We no longer do that. We only use geom bar for making histograms when we've got discrete variables, and the code is really simple. You just say geom bar, and you ask it, hey, what's the variable, the discrete variable for which you want the number of counts? So if I specify x is equal to drive, I can see if I look at here that I've got, in fact, 103 records here, 106 records here, and 25 records here. for these 3 different drives. Faceting. Faceting allows us to create separate panels, and we'll see 2 ways to do this: facet grid and facet wrap. Now, when we went over histograms, we produced a plot like this. And I began that topic by saying that, what I really wanted to do was to look at the effect of the different drives on the distributions of highway mileage. And then I said, no, I'm actually lying. When I look at histograms, I'm only going to look at the front-wheel drive vehicles, but eventually it would be clear what I was going up to. And now we finally are able to resolve that problem. How do we compare histograms for the 3 different drives? And the way we're going to do that is by faceting. So what I'm going to do is I'm going to create a series of panels. I'm going to have 1 panel for the 4-wheel, 1 panel for the front wheel, and the 3rd panel for the rear wheel drives. In order to do that, the function that's going to be used is facet grid. So the general syntax is shown here. So facet grid produces a grid with row and column names. So there's my facet grid function, and it's open and it's closed parenthesis. And I first specify the variable that I want on the rows, and then there's a tilde. And the tilde, if you look at your keyboard and you go to the upper left-hand corner, you find the escape key. Directly below that, you'll find the tilde. And then you specify the column variable. It may be that you only want a single row, but multiple columns. There's facet grid, and if you only want a single row, in that row location, that's the row location is the first location, you specify a dot, and then you specify the variable you want in the columns. Alternatively, if you just want 1 column and multiple rows, there's the facet grid with its open and closed parenthesis, the row variable you specify, and then in the position where the column variable should be, you have a period, and again, separated by a tilde. So, we're going to play around with this a bit, and the first thing I'm going to do is create a data frame called MPGK, which is just like MPG, except I've tossed out the 5-cylinder engines, and we'll see why I'm doing that in a moment. So I'm going to have this modified data frame, and I'm going to make histograms. And remember, the code for making histograms is really simple. If I want histograms of city mileage, all I got to do is say map the X location on the city, because recall with geom histogram, it's got that default stat, which is bin, and that's going to take this continuous variable city, chop it up into bins, count the number of records on each bin, and that's what's going to go on the y-axis. So there's no specification of y equals that's required, because stat equals bin is going to take care of that from us. So we're going to have these histograms. Now, in order to make our facets, we're going to add as a layer the facet grid function. And so what I want is, I want to have drive on the rows, and I want a single column. So in the row position, I put drive, there's my tilde, and then a period in the column position. So I get drives on the row. So on the rows, I've got different drives, period here, single column, I've got a single column. Now, there's another way I could have made this plot. Another way I could have made this plot was first have created an object called plot that had the plotting function and a layer that says, hey, make me histogram of city mileage. And what we're going to do is we're going to take advantage of this whole idea of creating and modifying plot objects. So once I've got this object plot in hand, if I want to make this plot, once I've got the object plot, all I need to do is add the facet grid function. And the reason I'm going over this is that in the next series of slides, what I'm going to do is I'm going to start off with plot, I'm going to add my facet grid function, and I'm going to look at different configurations of what's going on in here and see what effect it has on the plot. Actually, before I go on, I'll mention one other thing. Typically, the way I write my code is like this, with facet grid appearing at the very end. Now, although facet grid appears at the very end, in my mind sometimes it's easier to understand it if I begin by thinking about facet grid. If I think about what that function is telling me, what that function is telling me is make a series of panels. make a series of panels with drive on the row and a single column. The period is going to give me a single column. So this facet grid says make a series of panels with drive on the row and a single column. Then everything else indicates, well, what goes in each one of those panels. What goes in each one of those panels is a histogram of city mileage. So recalling that we've created plot by using this code, I can make this chart here by starting off with this object plot and adding to it the facet grid function. But now I've just switched around relative to the previous slide, the period and the drive. So now in the row location, I've got a period. So I get one row, and in the column location, I specified drive, so now I'm going to have drive on the columns. In here, I've started off with that object called plot. I've added facet grid. I'm actually going to take advantage of the fact that it can represent a grid of variables. I've got drive on the row, so there's the three different drives sitting on the rows, and I've got cylinder, sil, sitting on the columns, and you've got the 4, the 6, the 8. There are some 5-cylinder engines, but remember in MPGH I dropped off the 5 cylinders, and the reason I did that is there aren't very many and it made the chart look really ugly. So now what I want to talk about is how we can use facet grid when we've got nested variables. And just as a quick review, let's remember the distinction between crossed variables and nested variables. So I've got different experiments or different data sets in which I've got two different variables. And those two different variables can either be nested or crossed. And here's an example of crossed. So we've got this experiment where plants are fertilized or not, they're watered or not, and the whole idea about a cross design is that all possible combinations are present. So I got some pots with nitrogen and water, and some with phosphorus and no water, and some with no fertilizer, no water, etc. So all possible combinations are present. In contrast, when I've got a nested design. So in this particular case, I've got model is nested within manufacture. And if model is nested within manufacture, then each model is associated with one and only one manufacturer. So Expedition is only associated with Ford, and Civic is only associated with Honda, etc. So my goal is to make a plot that looks like this. And in this particular case, I'm only interested in 3 different manufacturers, the Ford, the Honda, and the Hyundai. And I have models that are nested within manufacturers. So Civic is associated only with Honda, and Mustang only associated with Ford. And the variable that I'm interested in is average city mileage. So that's the plot that I want to make. So in order to make that plot, as often is the case, we have to begin by making the data frame. So I start off with MPG. And I'm only interested in these 3 vehicles, or 3 manufacturers, Hyundai, Honda, and Ford. So here's some code that'll do that, and you can refer to your manual if you've forgotten how to do this code. So I specify manufacturer, and this is just a recipe, percent in percent. Then as a vector, I indicate the manufacturers that I want to retain. They're, of course, inside quotation marks because these different variables are characters. So that will filter my data, so I've only got those 3 manufacturers. Then I'm wanting a summary data frame, so I group by manufacturer and also by model, so I have the different combinations of manufacturer and model, and then I get this additional variable, city average, by using the summarize statement. City average is calculated as the mean of city mileage. So once I've got that data frame, once I've got the data frame that I just created, MPG nest, I'm going to try to make this plot. And as I said earlier, in my mind, although it occurs at the bottom of my code, I'm going to start here. I'm going to say, okay, I'm going to use the facet grid function. In the row position, I've got a dot. So I'm going to have one row, and then in the columns, I'm going to have manufacturers. So we've got one row, and on the columns, I've got my manufacturers. And then I think, okay, what's going to go inside each one of those panels? So I've got a grid of panels. What's inside each panel? What's inside of each panel is a column plot with model on the x-axis and average city mileage on the y-axis. I write all that code, and we can see we got a huge problem because for all 3 manufacturers, I've got all 7 models listed, and obviously that's going to give me a whole bunch of blank space. Also worth noting that if I want to get these titles here on the x-axis, there's the code that does it. So this is axis text x here. That's the name of that element. So I specify the axis text x. Specify axis text x. It's going to be operated on by the element text function. I specify the angle is equal to 90. Through trial and error, I've said if the vertical justification or VJust is equal to 0, horizontal justification is equal to 1. That seems to work out pretty well. But you need to address the problem of this blank space. And this slide and the next slide are essentially just recipes that are going to demonstrate how to take care of that blank space. So the first thing we're going to do is, within our facet grid function, we're going to say, okay, want a single row, want manufacturer in the columns, and this is entirely in Courier, scales equals free x, and that does a nice job of getting rid of that extra space. It creates, however, a secondary problem in that these bars are of unequal width. So to fix that, in addition to scales equals free x, we also add, notice, all in Courier exactly like this, space is equal to free y, and we get something that looks pretty decent. So remember, this symbol here was meant to identify those slides, 5 slides in this manual, in this lab, that are really the most important, and this is the 5th and final of those. And this shows the 4 different type of geomes that can be used to examine distributions. And I wanted to wait until now so that I can present this one, which shows how we can represent for each of the different drives. We can compare drives, compare their histograms. So in terms of the geomes we've got to look at distributions, it goes from the most detail to the least detail. And the geome that gives the most detail, my personal favorite, because it does give the most detail, is geome jitter. And the nice thing about geome jitter is that all 234 points in the data frame are shown here, and the Y value reflects the actual highway mileage. We've introduced some jitter in the horizontal direction so we can actually see what's going on. We don't want to have any jitter, obviously, in the vertical direction. And then we lose a little bit of detail with geome histogram and with geome dot plot. Why? Because we've created bins. So this continuous variable highway in both cases, or excuse me, in this case, the continuous variable highway gets chopped up into bins. You get the count of the number of observations in each bin, and that's what goes on the y-axis. In the case of geome dot plot, you've got this continuous variable highway that's chopped up into bins, and there you've got these bins that are oriented relative to the y-axis, which is why you had to have that bin direction equal to y. And then finally, with the least detail, essentially just presents summary statistics, is the box plot. So the box plot presents the summary statistics of the median, and then within the box here, you've got the values that comprise 50% of the records that fall for for rear and front wheel drives. 5B is just a slight switch on 5A. All I've done is focused on the orientation. So with these 3 types of plots, we've got drive on the x-axis and mileage, highway mileage on the y-axis. But as we go from this direction downwards, we're losing detail. This is my favorite because it's got all the detail. The y value reflects the actual highway mileage. Here you've lost detail as a consequence of making the bins, and here all you've got are summary statistics. So this is one orientation. The other orientation is shown here. We've taken this continuous variable highway mileage, chopped it up into bins, put the count of bins on the y-axis, and we show our different drives by using facet grid to put those drives on different rows. So We just went over facet grid. Now I want to talk about facet wrap. And the difference is that facet grid specifies a row variable and a column variable, although you could put in a dot if you wanted to have only a single row or a single column. Facet wrap, in contrast, has only a single variable. So what happens is it produces a string of facets that has some wrapping. So what I want to do now is produce a plot that looks like this. And again, although it comes at the bottom of my code, conceptually I often start by thinking about what this facet function is going to do. So in this case, I've used the facet wrap function. So there's the facet wrap function, and it's open and it's closed parenthesis. And this strikes me as being a bit strange because there's a tilde required. And I'm not really sure why that tilde should be required, because with facet wrap, unlike facet grid, you're only permitted one variable. So I'm not sure why the tilde is required, but it is, so we're going to put it in. So the whole idea is when I've got this at the end, I'm telling R, make a series of panels. Make a string of panels. Make this long string of panels, but then wrap it to make it as square as possible. So that's what this last line is telling me. But then the question is, okay, what's going to appear in each one of those panels? What's going to appear in each one of those panels is going to be a histogram of city mileage. So that's the code that does it. The only disadvantage of that previous block of code was you notice there's this kind of gap here and it looks pretty ugly. So one way to get rid of that gap that appears here is to recognize that in fact there are 15 different combinations or 15 different manufacturers in this data frame. So if I want to make something that appears rectangular, I can easily do that by specifying ncol equals 3. So this isn't truly a grid. It's not truly a grid in the sense of having a grid with some column variable and some row variable. It's actually just a long string that's been wrapped. But I can specify the configuration by setting ncol is equal to 3. I've got something which sort of has these 3 different columns, and it looks very nice given that I've got a total of 15 different observations. So now I want to switch topics and think about, okay, if we've got a scatter plot, how do we produce a line of best fit? And that's going to be accomplished by adding the stat smooth function. So the organizing principle behind these last 5 labs has been the whole idea that we've got this plotting function here, and then we add to it a geome. And every one of these geomes has these 5 different things: the data, the aesthetic mapping, the options, the stat, and the position. It turns out that there's an altogether parallel universe that would begin with a plotting function, and now instead of having a geome, we're going to have a stat. And whereas every geome has a default stat, every stat has a default geome. Now, in preparing this lab, it occurred to me that this was probably the best template, and that we really didn't have to worry about this. We really didn't have to worry about this or to think about this whole idea of stats. We didn't really have to think about stats until now, and now we're going to think about stats. So the general format for stats is the word stat, underscore, and then something there. So the only stat that we're going to consider is stat smooth. These are a whole bunch of stats that we're not going to consider. The only exception to that is if you go to Appendix A1, you can see stat summary, and that's the stat that you'll want to use if you're going to make a box plot and you want to add the mean to it. Because you remember, by default, box plots only show the median and not the mean. So this is just an overview slide. An overview slide of how we're going to add a line of best fit to a scatter plot. And we're going to take advantage of the fact that ggplot2 is a layered language. We're going to have this layer here, the plotting function, and we're going to add with a plus sign this layer here to make the scatter plot. and then we're going to add with a plus sign a bunch of stuff here to add the line of best fit. So within our plotting function, I'm going to specify both the data frame and also the X and Y variables. Now remember earlier on, we saw a slide that looked like this. It said that most of the time, this is the way we were going to do business. We were going to specify the data frame within the plotting function and the aesthetic mappings within the geom. But occasionally, what we'd want to do is put all that information inside the plotting function and have it inherited by the geom. And that's what we're going to do in this particular case. We're going to put all that information inside the plotting function. Now, why would I want to do that? Well, the reason is that irrespective of whether it's the scatter plot or the line of best fit, both of those things need to know what the X and the Y variables are. So I'm going to save myself some typing by putting it up here, and it's going to be inherited both by my scatter plot produced by geom point and by the line of best fit produced by stat smooth. And then I'm going to add as a layer geom point, and I can put whatever sort of features, the size, the color, whatever, specified within that geom point, whatever I want. And then I'm going to add my stat smooth. And stat smooth, I'm going to present in this kind of template that shows the 5 things that are associated with a stat. The data is going to be inherited. The aesthetic mapping. Well, I don't need to worry about the X and Y mappings because those are going to be inherited. But the thing to remember about stat smooth is that every stat has a default geom. And the particular default geom for stat smooth is going to be a line. So you think about some of the mappings we've previously seen for lines, they could be things like color or line type. We might think about mapping those to change the features of our lines of best fit. And then we come down here and look at the options. And we've got a bunch of options that are specified here, although the first 2 really aren't that optional. We're going to need to specify a particular method. And in this lab, we're going to think about 2 methods. One is LM to give a straight line, and a second is method equals NLS if you want nonlinear regression. And you're also going to have to specify a formula equals to determine the relationship between the Y and the X axis. So you can also remember the default geom is a line. And so as options, you might want to specify things, set things such as color, size, or line type. So that's just a general overview of how we're going to have a layer scatter plot produced by geom point, then superimpose on that a layer line of best fit generated by stat smooth. This is just for folks who have used R before. If you haven't used R before, you can just ignore this. The method we're going to use statistically is LM, and that's the method is used for simple linear regression. And if you've used R before for simple linear regression, you should be familiar with the output that it produces. Okay, so here's the actual code. So there's my plotting function right here. And as before, I mentioned, do the aesthetic mapping of the X and Y. And the reason I'm going to do that up here is it'll be inherited by both geom point and by stat smooth. There's enough information here to make a scatter plot, so I don't need to put anything inside those parentheses. I'll get a nice little scatter plot. Then I add as a layer stat smooth, and the simplest case, all I get to specify are those 2 kind of non-optional options. I have to specify method equals LM. It's all in Courier, and what that's going to give me is a simple single straight line. Formula Y tilde X. Put it in exactly like that in Courier. What's going on? Well, what I want to know is the linear relationship between city mileage and highway mileage. So up here, I've said that Y is equal to city and X is equal to highway. So if I want the linear regression, city is equal to some function of highway, I've set up here that city is the y variable, highway is the x variable, and then I put formula y tilde x, and that will give me city mileage as a function of highway mileage, the straight line that reflects that relationship. There's this little gray line here that apparently is referred to as a confidence interval. I don't know exactly what that means, so I'm not going to use it. So this is essentially the same code as before, but with a few little modifications to improve the appearance. So there's my plotting function, specify the x and y mappings. All I've done here is inside GeoPoint, I've set the size equal to 4 to make these markers a little bit larger. Then I add as a layer my stat smooth, method equals LM, formula y tilde x. That's pretty much required. Then I'm going to do some additional settings because recall that with stat smooth, the default geom is a line. So I got this line, so I can set the features of the line. I've done so. I've set the size equal to 2 to make it a little bit thicker. I've set the color to be equal to red. You can clearly see that here. I set the line type equal to 5 because you remember from previous slides, line type equals to 5 gives me that long dash. I've also specified s equals false to get rid of that little gray line because I really don't understand it. So in the previous slides, we saw how we can include a line that shows a simple linear relationship between two variables. And now we're going to think about how we can include a line that shows a nonlinear relationship between two variables. And in this regard, I would argue that R is going to be a whole lot more powerful than Excel. So if I look at this particular scatter plot, it shows the relationship between city mileage and the displacement. It looks to me like there could be an inverse relationship in the sense that city mileage is inversely proportional to displacement. So again, inverse relationship here. So how could I insert a line of best fit that shows that? And that can be done by using the method NLS that involves non-linear lines. So if I think about this relationship, city is inversely proportional to displacement. Another way to think about that is my y variable is inversely proportional to my x variable. And if I wanted to state that as an equality, then I could say that y is going to be equal to some constant b plus a over x. And with that in mind, I can think about how I could produce this plot. So ggplot2 is a layered language. I'm going to begin with my first layer, which is the plotting function. I'm going to state what my x and y variables are. Stating those within the plotting function, they can be inherited by both GeoPoint and StatSmooth. I don't really require any additional information within my scatter plot, but I've decided to set the size of these markers equal to 4 to make them somewhat larger. I'm going to change the method. The method is no longer going to be LM. The method is going to be NLS because now what I'm doing is nonlinear regression. And I would emphasize that the ability to do nonlinear regression really makes R stand out relative to, let's say, Excel. So, specify the method, and then I also have to specify the formula. So how do I specify the formula? It's based on this assumed relationship here, that y is equal to some constant b plus some constant a divided by x. And it's worthwhile thinking that y and x are city mileage and displacement, and a and b are two constants that are going to be needed to be estimated. So with that in mind, there's this other line here that again you can just think of as being a recipe. And the important point about this recipe is that again we think about this distinction between y and x, which we define as city mileage and displacement, and b and a that are coefficients that need to be estimated. So the way that nonlinear regression works, and we're doing nonlinear regression with method equals NLS, in order to come up with our estimates of B and A, we need to give it some starting points, some starting guess of what A and B might be. And we just use this recipe here to tell it what our initial guesses of A and B are going to be. And so having fed it that information, then what this method NLS is going to do is it's going to use an iterative process to try to come up with its best estimate of A and B. So that's really the guts of this. And then after that, followed by a comma, are some additional settings that I use just to make this plot look nice. Again, the default geome for stat smooth is a line, so I've set the size as equal to 3, I've set the color equal to red, and then I've also used this SE equals F so I don't have that irritating little gray line.